I'm going to talk a little bit about binary trees. This is a more advanced data structure than what we've been seeing with the linked lists, the stacks and queues, and even things in the standard template library. So we've seen quite a few data structures in CS150, starting with arrays, and then moving on to vectors and lists, stacks and queues. And in looking at vectors and lists, they're great for lookup due to the indexing and sorting for vectors. But the insertion can be quite expensive because you have to move things around within the vector, and that can be quite time consuming in terms of computer time. Lists, on the other hand, they're great for insertion. It's very easy to put something into a linked list as long as you remember the order that you're doing those pointers in, but the lookup can be expensive. So even if you're maintaining order, you have to do the lookup. So, you can kind of see where we're going with this. We want, some type of compromise where we have both great lookup, but we also want to have great insertion. And the answer to that are trees. So a binary tree is either empty or has these properties. One, it has a root node, and then it has two sets of nodes, a left subtree and a right subtree. And both the left subtree and the right subtree are binary trees, so this is a recursive definition. Every node has at most two children, and a node stores its own information. It keeps track of its left subtree and right subtree using pointers left link and right link. So if you want, you can look at the code that I've put on Lima under the resources under code for the binary tree. Or we'll talk about a little bit of a lighter weight implementation that I have on Geeks for Geeks. Obviously, Malik tends to go with these very heavyweight classes, starting with an abstract container class and then with the specific implementation of the class. So the implementation on Geeks for Geeks is a little bit more lighter weight, and we can see the kind of the structure of the tree without delving too much into the details. We'll get into those details a little bit later in the lecture, but for right now, basically we have a struct, which is a node, and inside the node it has the data, the value. That's currently an integer, but you could make more descriptive data if you would like. There's also a left pointer and a right pointer, and you can find this in the associated lab, or if you're looking for Malik's code, you can find it in the associated lab or under resources. So the first thing we want to do is we want to make a new node. So in order to make a new node, we allocate memory for that node, and here they use malloc instead of new, but that's 6 of one, half dozen of another. I prefer the new command. We assign data to that node, just like we do with our nodes in linked lists or stacks or queues, and then initialize the left and right children as null. So basically, this just has a single node. So that creates a new node, and the new node doesn't have any left or right pointers. Now, once we take the new node and we turn it into a actual tree, then we can do that by creating the root, and we start at the root. So we say struct node root is equal to new node, and we give it the data 1. And so the structure of the tree after that statement will be a 1 with a left tree of null and a right tree of null. Then we can set the root's left to be 2 and its right to be 3. And because we've created those new nodes, we now have a tree with 1 on the upper level for the root, 2 is its left subtree, and 3 is its right subtree. 2 and 3 are both trees with left and right subtrees equal to null. So, a lot of times we're representing these binary trees graphically, and the 3 lines here means that you have a null pointer. So that's the leaf of the tree. And typically we include a pointer to the root node that's outside the binary tree. So here's a pointer to root, and it points to the node with A, and A has a left subtree beginning with B and a right subtree beginning with C. That's how that works. Other terminology, I mentioned leaf. That's a node that has no left and right children. U is said to be a parent of V if there's a branch from U to V. And there's a unique path from the root to every node within the tree. So there's a way to get to every single node within that tree starting at the root. And the length of the path is the number of branches on the path that you take from the root to the particular node you're looking for. And then the level of the node is the number of branches on the path from the root to the node. And then the height is the number of nodes on the longest path from the root to the leaf. And we can find a lot of these things with recursive algorithms. So let's take a look at algorithms on a binary tree. And as you might expect, when you're looking at Malik's code, and again, I have that under the code section of La Lima, you'll see a lot of recursion. The other thing you'll see is binary tree is a dynamic data structure. You allocate and deallocate memory at runtime, so it's useful to have a copy constructor, an overloaded equal, and probably a destructor if you're, in some way passing your tree to a function. Using just the value of the pointer of the root makes a shallow copy of the data, which is something we don't want because the copy points at the exact same thing. To make an identical copy, we need to create as many nodes as in the original tree and copy those over. And we can actually use a recursive algorithm for that. So let's look at copy tree. So if the tree that we're copying from is equal to null, it's an empty tree, well, then the copy tree is null. Otherwise, the copy tree root is equal to the one that we pass to it, and we then recursively copy the left tree and the right subtree. So basically copy the root, copy the left subtree, and copy the right subtree, which is a nice recursive algorithm, and it will go through and do that by pushing everything onto the stack, and we don't have to worry about managing that or traversing it. Speaking of traversing, and you need traversing when you do things like insertion, deletion, lookup operations, or printing out the tree, you'll need to do a traversal. There are three types of traversal. One, in order, you traverse the left subtree, then you visit the node, then you traverse the right subtree. So if we're doing the in order, we would go from A, visit the left subtree, that takes us to B, visit the left subtree, D, there's no left subtree, so we visit the node for D. Now we go visit the right subtree, which is F. Then we go back up, B, up to A, then over to C. There's no left subtree, so we go over to E. There's a left subtree. We visit G, and then we go back up and visit E last but not least. Pre-order, we visit the node, then traverse the left subtree, and then the right subtree. And then post-order traversal, we traverse the left subtree, then the right subtree, and then finally we visit the node. So make sure you know how to do those types of binary tree traversals. I know we cover them in 141, 241, so this hopefully it looks pretty familiar to you. Let me know if it's not, and we'll spend a bit of time going over it in class. Other operations, determining whether the binary tree is empty. That's pretty easy. If root is equal to null or null pointer, you got an empty binary tree. Searching the binary tree for a particular item, insertion, deletion, finding the height of the binary tree. That one's a nice recursive algorithm. Number of nodes, number of leaves, the three types of traversals, and copying the binary tree are all explored. So when you look at the code from Malik, you're going to see a number of different things, and this is why we cover a lot of the stuff we cover in 151. You'll notice that there are the big three member functions. There is use of virtual functions, so we have an abstract class that is a container for the entire set of different types of binary trees. There are private member functions, protected member variables, recursive functions, and templates. So there's a whole heck of a lot going on. In terms of the private member functions, that's maybe something we haven't seen before. These implement public member functions to the class so that the call needs to go through the class itself. So this is, additional bit of data protection. And the recursive functions make it a heck of a lot easier to implement than the non-recursive versions, because the non-recursive versions require external data structures such as stacks and queues. And of course, the template class is used to promote data abstraction. Big three, because you have dynamic memory, and the virtual functions are because there are several specialized types of binary trees. So how you search, sort, insert, delete are specific to each subclass. Whether it's in order, balance, you're going to see a whole heck of a lot of trees in 321. So anyway, that's a wrap. And next time we're going to look at how we actually implement those virtual functions and how those work. So thanks for listening to this short one. I appreciate it.